Hello, my name is Aran Santiago, and I'm going to talk about publication of secondary analysis from randomized trials in critical care. The recent proposal by the International Committee of Medical Journals editors requiring authors to identify individual patient data publicly available within months of publication of a clinical trial has generated much debate.
So the goal of the randomized control trial is to determine or to test the efficacy of a treatment or an intervention. And the way you do this is you'll intervene in one population, and you'll compare that intervention to the outcome in another population that didn't have the intervention. So let's look at an example to make this a little clearer. So let's say we start with 100 people, and I'll just denote this by this stick figure right here on the top left. And I've already drawn in the population here. And let's say that each of these different colored people represents 10 individuals. So we have a diverse slice of the population. And the idea is we're going to break these into two groups. And let's say this first group here is going to get a drug, which we'll call drug A. And the second group here isn't going to get a drug. And this population of 100 is going to be divided into two groups of 50, which I've drawn in here. And ideally, it's going to be divided so that each population has a similar population breakdown. So there's an equal number of similar individuals with similar characteristics in each population. And this is going to be done by the experimenter. So I've drawn in here this guy in a white coat symbolizing the experimenter. So since these populations are similar to one another, we can then compare drug A versus no drug. So I'll just write in the word compare. And we can tell which drug is better, drug A or no drug, and that's going to lead us to our conclusion. So we might be able to say that in this case, drug A works better than no drug in, say, lessening whatever treatment you're looking at here. So we'll just say A works out better in this case. So there's a couple of parameters of randomized control trials that we just want to get down on the right half of the page here just to make sure we got them down. And the first one of these is randomization. And we said in our last video that randomization was the experimenter deciding which drug population individuals are going to fall into, in this case drug A or no drug. And we know that's assigned by the experimenter, this guy in the white coat here, so I'll just write EXP next to him to make sure we know that he's the experimenter. So the next parameter of RCTs we're going to look at is that of blinding. So blinding is extremely important in randomized control trials.
The debate has focused on opportunity costs to the scientific community and the appropriate time frame for the primary investigators to conduct and report secondary analysis.
Hello and welcome back to this Global Health YouTube channel. My name is Greg Martin. We're in the middle now of doing a series of videos on research methods and study design. In the last video we looked at case control studies and cohort studies. In this video we're going to look at randomized control trials, and we're going to take a look at the idea of confounding and talk about why it is that randomized control trials are so good at controlling for confounding. The starting point is we take a group of people who have now volunteered. These are trial participants. They've said, yes, we will participate in your trial. And we randomly assign them to two groups. Now, it's important that they're randomly assigned to the two groups because what we want is we want these groups to be similar in every possible way. The one group gets an intervention. That intervention might be a drug. It might be, there's a number of things can it be. Keep in mind that randomized control trials don't have to have people, individuals, as the subject of interest. They could be communities. It could be a hospital. But for the purpose of this talk, let's imagine that these are people we're talking about, right? So the one group of people get an intervention. They get a drug that we're trying to test. The other group get a placebo or a non-intervention, right? But we give them a placebo. And then we follow these two groups up and we analyze the data. We compare the data and we see if there's any difference between the two groups over time. One of the problems that they solve is the problem of confounding variables. And let me just try and explain what a confounding variable is. A confounding variable really is an alternative explanation for a relationship that we've observed. So let's imagine, for example, that we've noticed that with an increase in shark attacks, we see a corresponding increase in the sale of ice cream. We must assume that there's some alternative explanation for this relationship. And the alternative explanation really is what we call a confounding variable. And in this case, it'll be hot weather, right? So as the temperature improves and it becomes summer, people will be swimming in the sea more and they're going to get bitten by sharks. At the same time, as the temperature goes up and it becomes summer, people buy ice creams more. And so we could erroneously assume that there's this causal relationship between shark attacks and eating ice cream, but that's not the case. There's an alternative explanation. The important thing about confounding variables is that they must be associated, or they must be connected with the exposure and the outcome of interest, but not on the causal pathway. And that's what a confounding variable is. So the reason that randomized control trials are so good at dealing with this problem of confounding is that if you've got some sort of variable that would skew the relationship between an exposure and an outcome, but that variable is equally distributed in the two groups that you're considering, so the intervention group and the placebo group, both groups are equally affected by that confounding variable. And so when you compare the two groups, the effect of that confounding variable is nullified. And the beauty of a randomized control trial is you don't need to know what the confounding variable is. Because the two groups are equal in every way that we can imagine, confounding variables that we haven't even been able to envision are controlled for automatically in a randomized control trial. Beautiful stuff. Thanks for listening. I hope you enjoyed this.
There are scarce published data on the publication rates and factors influence this rate, and the time taken to publish secondary analysis from clinical trials.
This video covers randomized controlled trials, or RCTs, which are one option to consider when planning an impact evaluation. Before deciding to use RCTs, you will need to consider the building blocks of evaluation, research design, data collection and analysis, and synthesis. RCTs measure the impact of an intervention on a particular outcome by conducting a carefully controlled experiment to compare at least two groups, one which has received the intervention and one which hasn't, known as the control group. For example, UNICEF recently funded a trial of early child development intervention in Pakistan. The trial aimed to evaluate the effectiveness of early childhood interventions to strengthen and improve the health outcomes of young children. Hundreds of children were randomly selected at birth from a number of rural catchment areas to be part of the RCT experiment for a period of 24 months. The selected children were then randomly assigned to either the intervention groups or the control group. The process of random assignment to create these groups is a key feature of an RCT. Without it, it wouldn't be an RCT. In a simple RCT, a single intervention group is compared with a control group. The results of the evaluation are determined by comparing the progress of the intervention group against the control group. More complicated RCTs can have more than one intervention group. In the Pakistan example, there were 3 intervention groups, each receiving a different set of treatments. The first intervention group received nutrition counseling, responsive feeding advice, and nutrition supplements from 6 to 24 months of age. The second intervention group received stimulation and care for development advice, including coached practice, integrated in routine monthly home visits and group meetings. And the third intervention group received a combination of both the early childhood development and the enhanced nutrition interventions. They were all compared to each other, and also the control group, which had no new intervention. This design, in which a third intervention group receives both interventions, whilst the other 2 only receive one, is called a factorial design. The inclusion of this third group allows us to study the individual effect of all the interventions as well as their interaction with others. A factorial design can have a number of groups and variables and is not limited to the combination shown in our example. In this RCT, the children were sampled as individuals, but sometimes participants are randomly sampled as groups, for example by school or village. This is called a cluster RCT. Back to our example from Pakistan. The children's development was monitored against several.
Research the New England Journal of Medicine and the Lancet over an 11-year period from January 1, 2000 to December 31, 2010 for published randomized controlled trials in critical care medicine.
trials have been used mostly in medicine. They've become very, very widely used in economics, but also in other social sciences. Evidence-based policy is one of the magic words of the day. And while everybody thinks evidence is a good idea, what we argue is that there's no special status attached to randomized controlled trials, even though a lot of people think they should have a special status, and that evidence from randomized controlled trials is somehow better than other evidence. Usually, for instance, when we do economics, you have to control for other things. So if someone has more money than others and they behave differently, it might be because they have more money, they have more education, they might be a man versus a woman, they might be lots of different things. And a standard economic procedure would be that you have to control for these various things. In randomized controlled trials, it sort of looks like you don't, because the rhetoric would say something like, the only difference between these two groups is the treatment because they've been randomly assigned. And that's a pure misunderstanding. Randomization does not equalize the two groups. So what you'd really like is the two groups are balanced on all these other things that matter. And there's no way that randomization guarantees that. More fundamentally, there's the question, even if you've got a good estimate from a trial like that, what use is it actually in policy? And how could you take it from, it worked here to will it work somewhere else? Or will it work when the government requires all schools to put that policy in place? Will it work in Kenya just as well as it worked in Wales? It's what Nancy Cartwright likes to call helping factors. If a policy is going to work, it often needs an environment in which it can work, and it won't work in another environment. And the randomized control trial doesn't tell you anything about that. It just tells you it worked in one place. The key takeaways I would categorize in two parts. The first point is that there's nothing magic about randomized control trials. It's not like this is the washing powder that washes whiter than any other washing powder. It has advantages, it has disadvantages, so do all the methods we've ever used, and we have to be aware of those. The second thing is that if you're going to be serious about using them for policy, which is what people think they're going to do, you have to ask the question as to, when you do the experiment, how do you transfer the result to the policy setting? And for that, you have to think about that before you run the experiment.
In randomized controlled trials in critical care medicine that were published in the ICMJE journals with the highest impact factor, a substantial proportion of trials do not produce secondary publications.
And that's denoted here. So all the blue people who live in cold weather are grouped together because of some characteristic that the experimenter can't control, and the same for people who are grouped together because they live in hot weather. So this parameter of randomization is what determines the difference between an experimental study, which has randomization, and an observational study, which does not. Now we can further break down observational studies into two different groups: descriptive studies, which are right here in green, and analytic studies, which are right here in purple. So what's the difference between a descriptive and an analytic study? Well, it really looks at what type of questions they answer. So an analytic study, for example, is going to answer the question, why? So if we were to take this population of people who live in hot climates and do an analytic study, we might ask the question, why is there an increased risk of, say, lung cancer in this population that lives in hot weather? And when we do our study, we're looking for the reason why this population has an increased risk of lung cancer. A descriptive study, on the other hand, asks a different set of questions. It looks at who, what, when, and sometimes even where. So if we were to take, for example, this cold population and do a descriptive study, we might look for the number of cases of lung cancer that appear, or where they occur, or who they occur in, older people or younger people, for example. So it's a different type of question between a descriptive study and an analytic study. The British doctor study looked at who developed lung cancer, those who smoked or those who didn't.